The floor is.
Well, thank you. Thank you very much for the kind introduction. I'm Cengiz Pehlevan. We'll be talking about basically scaling. I mean, we all know that we are living in a special time, right? AI is changing the world. All from language models to applications to science and image processing to generative models. Tons of things are happening. It's hard to keep up with, what's happening. And it's even harder to predict what's going to happen in the future. Now, the question about my task is, why is it happening? Why are things basically developing so fast? Has something new happened in the last few years that we discovered a whole new algorithm and I don't know, some new paradigm that basically led to this AI advance? And this is all probably true. There has been lots of technical innovations. But there's one dominant paradigm basically that seems to be working, in getting better and better and better AI. And that is the paradigm of scaling. So what do I mean by scaling? Actually, I mean not just scaling, the idea of predictable scaling. So what do I mean by this? And this is one of the first papers that sort of made a plot of the sort that I'm going to discuss and basically identified some trends which further led to basically what's going to be discussed. So the authors here were thinking about basically a neural machine translation task. And then but they're plotting on the y-axis. These are basically each curve uses models of different size. The minimum test loss, basically the performance of this model, is a function of basically the number of training data set size or the number of tokens that you give to this model. And then basically, there's some experimental curves and some curve fits and a similar plot over here. Anyway, the point is basically, these curves look regular in the sense that you could fit a simple parametric form and make predictions about what's going to happen in the future. Sorry, as you scale things up. Right? So that's already it's a simple idea that you can fit a curve to a bunch of points, but it also, identifies a trend that your performance gets better and better. That immediately raises a paradigm of getting to better AI. Just whatever the x-axis is, scale it up. So another relevant paper in this domain is this one, which was also very influential by Kaplan and colleagues, scaling laws for neural language models. So I like this particular figure because it makes comparisons of three different things on the x-axis. So now on the y-axis is again test loss. So this is basically the performance of the language model. So let's first look at the middle curve over here. So here what's happening is they're fixing a model. By that means fixing the number of parameters, architecture, and so on and so forth. And basically increasing the amount of data with which you train this model, so the data set size, tokens. And you again see basically a decrease in the test loss. It also turns out that, if you put this on a log-log plot, you can fit a line to it and you get an exponent, a power law, which will also play a role in this talk as we go on. But this is perhaps not surprising to us. As you give more data to a model, it should perform better. That's very intuitive, and that's what we expect it to do. Except, okay, that's what it is. Now this one, this was maybe at that time surprising. Maybe after you heard Andreas talk, it's not as surprising. But so the idea is basically it's the same model. It's a model. In this case, you're fixing the number of data that you give, but now making the model bigger and bigger and bigger. Okay. And then you again see basically a trend that gives you better and better performance. Again, in those days, this might have been a surprising conclusion because, if you if you fix a data set and make a bigger and bigger model, I'm sure there are physicists around here as well. That would be a terrible recipe. But however, you see an improving trend. Now, the first one is sort of a more important one because I think it more directly ties to money and cost. Okay. On the x-axis is the compute. What that means is the following. So compute is basically how many flops or floating point operations that you spend in training this model. If you throw it more data, you have to take more gradient steps. That obviously creates more compute. Or if you increase parameters, again, you have to take derivatives with respect to more things. That also adds compute. So both things scale up compute. What they were doing was this experiment. So each of these lines here, as you see, is basically one particular model of a fixed size. And then what goes, and as you keep adding more and more data, obviously the curve goes down and down. Okay? But at some point, these curves start saturating. So basically, there's a point beyond which adding more data helps, but not that much. So this is a smaller model. This is a larger model. Sorry, yeah, exactly. Yeah. So what you might also do is basically look at this Pareto frontier curve, basically the curve that takes the best model for a given compute, and then look at the trend over there. Okay, so that trend also itself gives you basically a power law or better and better performance. So this is called the compute optimal scaling law. The idea being that basically this was giving a recipe to people to basically get better and better models with bet for cheaper, for the best cost. Basically find the relationship between, as you scale your model size, scale your data set size as well, and then the relationship between how much you should scale both can be read from basically a combination of these two figures. Yeah.
So in this first curve, you are fixing both the model and also the data and only increasing the number of epochs, or?
So the training here is basically online, meaning you do one pass over the data. So you can read over data set sizes, number of gradient steps. Okay. So basically this is like both data and gradient steps for each curve. This is one particular way of doing it. You don't have to do it this way, but it seems to be a practice.
One small question. Like, how much does any point on this plot cost, like the time-wise or the money-wise? Like, let's say it's data size 10 to the 8 or 10 to the 9.
How much money?
Yeah, like either computationally or like the time-wise, like to get full size on this size of.
I don't really know about this, but I'll have some more numbers for something
okay.
coming. Yeah, I'll talk about that. For GPT models, I'll have some numbers for you. Okay, cool. I mean, so again, I mean, from maybe a mathematical point of view, it's not a big thing. You just collect a bunch of points and fit a line to it. But on the other hand, the implications are amazing, right? So basically, just as long as these trends work, you don't know how much this will continue, but it gives you basically a way of getting to better and better AI, perhaps AGI, whatever that means, right? So that's what it is. So this is scaling in training, meaning basically you're training a model from data from scratch. Nowadays, this is called pre-training or a foundational model training, whatever you want to call this. There's also there are other ways of throwing compute at models and making them perform better. So there's this recent notion of test time scaling. What that means is these are what's behind the reasoning models in GPT and so on and so forth. The idea is that you don't retrain the model, but what you do is when you're trying to, let's say you wrote a prompt, you're trying to get an answer, you make the model work harder. The way you would make it work harder is, for example, make it try to give you many different answers. And then you have a clever way of choosing a good answer among those answers and give that back to you. And then finding was basically that kind of a procedure would also improve performance. So for example, this is again a paper from these folks. And they were looking at the performance of an LLM on a math task. And on the x-axis is generation budget, basically how many different answers it was allowed to generate. And basically, you can look at these dash curves over here. As you generate more and more answers, your accuracy on the data set was getting better, right? So for example, this one, a majority, I think one of this is majority. Yeah, the dash ones are majority. What that means is basically, you let the model give you many different answers, and you choose the one that has the majority, majority agreement on them, for example. I mean, this is this also led to the, so now this is the reason why you're waiting a longer time when GPT is trying to give you and basically trying to do this. Okay, cool. So scaling is working, but an important aspect of it is, of course, predictable scaling. So this is an extract from a GPT-4 technical report. So a large focus of the GPT-4 project was building a deep learning stack that scales predictably. The primary reason is that for very large training runs like GPT-4, it is not feasible to do extensive model-specific tuning. So I'll talk about this in a second. To address this, we developed infrastructure and optimization methods that have very predictable behavior across multiple scales. These improvements allowed us to reliably predict some aspects of the performance of GPT from smaller models trained using 1,000 to 10,000 times less compute. Okay, so what do they mean by this infrastructure and optimization methods and model-specific tuning? I mean, of course, there are trade secrets probably, but this is what I think is happening. Every time you want to train a model, there's certain hyperparameters, right? For example, the learning rate parameter, and how you set that parameter matters, right? And there isn't really a good recipe for choosing them. So what you need to do is basically do a grid search. Now, if you have k hyperparameters, that's just hyper search in k-dimensional space. Obviously, this is going to be hard. And every search is basically one run of this model, right? So that's going to be a lot of compute. So many times, grid times the compute. So that's not good. So if there was a way of basically doing your hyperparameter search in a small scale with a much smaller model, and say find your best, let's say, learning rate in that model, and you had a way of extrapolating from that to the bigger model, let's say it saves you a lot of search and compute, right? So this idea is called hyperparameter transfer. Okay, hyperparameter and transfer because we're transferring from a smaller scale to a larger scale, and shows an example of an architecture, a neural network design such that this hyperparameter transfer works. I'm going to talk about the ideas behind how this works, but just to give you an idea of what this is. So again, we're plotting here test loss versus learning rates. This is a particular kind of a network ResNet trained on some data set C510 for a certain number of epochs, okay? And what we're plotting is basically the test performance after that certain number of epochs. For different models, so what's different here? On the x-axis, I'm varying the learning rate. And each of these lines correspond to a model with different depth and width. Width means how many neurons are, in this case, convolutional channels in a layer, and depth means how many of them I'm stacking, okay? And what you find is, so this is the shallowest and the narrowest model, so most compute efficient to do experiments. And this is the widest and the deepest model, so this is the most expensive one. And basically, if you design this network well and did your engineering well, you see that the optimal learning rate here basically corresponds to the optimal learning rate here. So you could do your grid search basically on this model and take that value and plug into the largest one, and basically this way save a lot of compute. So this kind of predictable scaling that leads to some consistency in hyperparameter choices is one of the aspects of basically making the scaling work. Any questions about this? By the way, I don't have to finish everything I want to say, so it's all right if you want to ask questions, slow me down, that's all good. Okay, cool. So this is a plot from that GPT-4 basically report. On the y-axis now, they're plotting against some performance metric, bits per word. I'm not particularly sure what that exactly means, but anyway, and on the x-axis, compute normalized by 1. So we actually don't know how many flops went to GPT-4. So that's one GPT-4 unit, basically. Exactly. But the idea is basically they did all these experiments, right? And then fitted this power law and then extrapolated all the way there. And then they expected, let's say, if I threw this much compute, my model behaved this way. And it actually did. And that's great success. Okay, so I'm just going through a bunch of slides before I go to the technical talk, but just to set the background. But this is all great. I hope to also give you a caution that not everything is predictable from smaller scale. That's also a fact. So for example, this is a very nice recent paper from these folks. What they were doing was basically they took a bunch of trained models at different scales. And instead of just looking at the test loss or cross entropy loss, they looked at performance on some tasks. These tasks have names here, some logical deduction tasks, some math tasks, and so on and so forth. And then these are correlation plots. I hope I have better resolution, but anyway, the plots are showing that on the y-axis accuracy and on the x-axis cross entropy. So how good this model was behaving versus, how good they're behaving on basically task itself. but the important point is not like if this goes up or down or anything, but the important point is there's like, for example, cases for tasks where you don't see any trend, okay? And then, there are also tasks where you see a breakthrough. What that means is basically at some scales, you don't see any performance, and suddenly there's a scale at which things emerge, right? The behavior emerges, which you would not be able to just by looking at smaller scale experiments, you won't be able to predict that's going to happen. And they have even like a chart here saying across 46 tasks, I don't know, 18 was predictable and so on and so forth. Okay, so this also then raises the question, are there challenges to this scaling paradigm? So is it going to go forever? Of course, data and compute hungry these approaches are. So this is a plot from some folks from last year. So what they were plotting is basically the effective estimated number of stock of tokens that exists in the universe. So this includes, I don't know, internet libraries and whatever it is, okay? And then this is years. And then basically the estimated amount of tokens that were used to train these models. And then, and they had some projection of like, how much, these models will scale. Anyway, so the conclusion from this figure was basically sometime around the end of 2027 or 2028 or something, we would have used all the tokens in the universe, so written things. So what do we do about this? So the previous trends about scaling tells us to use more and more data, right? So that's important. What's going to happen? Just to give you a sense of this y-axis over here. So if you were reading 100 pages per day for about 100 years, that's like 2 billion words. A word is like a token. Now a billion is like what, 10 to the 9 or something, right? So, and this is all starting from 10 to the 12 and so on and so forth. So this is already like a much more inefficient, if that's the way you want to conclude from this about the token stock. And of course, energy is another aspect of this, So, according to some rumor and other sources, GPT-4 consumed an estimate of 50 gigawatt hours of energy and took 100 days and cost $100 million. Okay. Yeah, exactly. And, and also per day, this is just the training part of this. And to just compare, a typical US household uses 30 kilowatt hours of energy per day. And this is just the training part. There's also the inference part. Every day, somebody's right. We are all using this. And an estimate was about 0.5 gigawatts per day. Just ChatGPT was using a lot of energy. Of course, it's no surprise that the companies are now investing in power plants and nuclear plants and so on and so forth. Yeah.
0.5 gigawatts was all queries in the day, or?
Yeah. This is some Forbes article, so I don't know where they got this number. So I'm hoping that it's not magnitude is wrong, but yeah, if you search Google, that's the number you find. Exactly. So that's how much this is the inference cost. Okay, cool. So this raises many interesting questions, right? So what are the limits of scaling? So I meant universality classes. Maybe I shouldn't have said it right? But just think about this, limits of scaling. How much we can scale, what properties are scalable predictably, and what properties don't. When does consistent behavior give rise to hyperparameter transfer? What sets these scaling laws, these power exponents? Like, what is that? Where does it come from? If you could figure that out, can we come up with more efficient scaling laws, meaning, better power exponents? This is important. At what scale new capabilities emerge? This has very important implications for AI safety, because the model might develop some dangerous behavior suddenly that you would have never predicted from doing these small runs. And is scaling sufficient? Will you reach AGI by doing this? Some people claim that GPT-5 signals the end of this era. Other people don't. I don't know. I have friends which subscribe to both ways. So I don't know. The point is there are many, many, many interesting questions that one can ask and study about this. Okay, so in the series of 2 talks, here's what I'm going to try to do. First, I'll talk about parameterizations for predictable scaling. So what that means is how to scale up a neural network such that they converge to well-behaved limits, things don't blow up or anything, and give rise to predictable behavior. Following up on Andrea's excellent talk today, then I'll spend a little bit of time saying something about what happens at these limits. And a tool that we'll be using to study that limit will be dynamical mean field theory. Andrea gave a great introduction. I'll say things orthogonal to what he said, so hopefully, there will be some repeat, but not as much. And basically, then I'll try to link from here to basically say something about the scaling laws and exponents itself. And the final thing I want to cover is basically, changing the topic a little bit, a toy model for emergence of behavior. And that's the idea of in-context learning, which you gave a great talk on. We'll talk about this. Now, this is an ambitious list of things. I will probably not have time to go through all of it. If I were doing this at a research talk pace, I would, but feel free to stop me, ask me questions. If I don't cover all of this, that's all good. The important thing is we just get some message across. Okay, so I just want to give some resources. So if you go to my lab website, my name.cs.harvard.edu, there's a resources link. And in that link, you will find a bunch of blog posts and lecture notes that I wrote for some summer schools and so on and so forth. That covers some of the things I'm going to say, not all, but this is a useful resource. Okay, cool. So let's think about parameterizations for predictable scaling. What do I mean by this? As discussed in Andrea's lectures, these three lecture series, previous work identified different behaviors arising from infinite, and this infinite can be width, depth, other things you could scale, attention head, whatever it is that you're looking at, okay? Limits of networks with different parameterizations and initializations. One set of limits go under the name of lazy, static, NTK, kernel limits. They all mean more or less the same thing. But the main idea here is basically networks in this limit do not learn internal representations of data. Okay, so that's where the link to kernels sort of come from. In many practical tasks that you look at, they show worse performance compared to the rich regime, which I'm going to talk about in a second. Just a parenthesis, you can create scenarios where basically they perform better as well, but not in practical things. Of course, this makes life easier in terms of analytical analysis. You can do some theories and so on and so forth. But of course, not realistic, meaning, it's not clear. It doesn't capture what happens in practice. There's other limit which leads to feature learning. People call this rich, also a mean field limit. They don't exactly mean the same thing, but they go together. Okay. The idea here is that network learns internal representations. Okay. So networks basically learning internal representations show better performance. Okay. Probably are more realistic. I'll comment on whether these limits itself actually capture what's happening in this compute optimal frontier at some point during these lectures. And another point I want to make is basically, even though I'm talking about this as like one thing, okay, even the kernel limit for a given architecture is unique, right? There's one NTK for it. The feature learning limits of an architecture is not necessarily unique. You might actually get different behaviors and so on and so forth, depending how we initialize and parameterize a certain architecture. So that's what I'll be talking about a bit today. Okay, but and then there are many authors and people that that studied these things. Again, talk by Andrea here covered beautifully what happens in two-layer networks. I'll try to say a bit more about deeper architectures and other architectures as well in these lectures. Okay, cool. Okay, good. So just let's start simple. So let's look at infinite width limits for MLP. So basically, what I'm trying to say is, how do I scale a neural network? By increasing its width. Okay, and the way I'll do this is basically just fix the depth. I'll fix it. So it doesn't have to be 2. It can be any finite number. It's just fixed. Okay, and then take the number of neurons per layer to infinity. Input will be a fixed data set. So I will not touch that layer. And output will be, again, given by that data set, so I will not touch that output. Okay, so this is just giving you the results before, because I want to show you some experiments before delving deep into this. So it turns out, I mean, there are sort of two, I'll call this universality classes of scaling here, meaning that like, there are two limits that you can define, different limits that you can define that leads to well-behaved behavior. And one is again of the lazy type, and the other one is of the rich type. So the difference between them is as follows. What you will do is basically like in all intermediate layers, you'll initialize your neural network by choosing weights from just a normal random variable and dividing by the square root of n, right? Of the n being the width of the previous layer, except that on the last layer, you will divide it by n, not square root of n. Okay? And there's a gamma zero factor here. We'll talk about this in a second. And then the learning rate, so if suppose we're doing gradient flow or gradient descent, okay, has also factors of some eta zero, this is an order one number. It has some other numbers, gamma zero, which we're going to talk about in a second. It might admit a factor of n as well. Okay, so what's the difference? So if you choose this gamma zero to be an order one number that does not scale with width, okay, this network is in the approaches a limit which is analogous to the mean field limit that Andrea described. And then this particular parameterization has a name. It's called the maximal update or mu-p parameterization. I'm going to talk about this in a second. If this goes like 1 over square root of n, right? So then basically this has the same normalization as the previous layers, and this guy cancels that guy. So learning rate is order one, it's not scaling up. Then basically this will approach the limit, the laser limit, which is called, and also this is called the neural tangent parameterization, yes. I'll fix, yeah. Yeah. Yes, I'll talk about that in a second. Sometime, yeah, so in an architecture, I'll show these things commute, but you can, but there are cases that you can create, they won't commute as well. Yeah, so, yeah, I'll say what I'll say. Let's see if that will be enough. Okay, cool. Okay, so we'll drive these scalings in a few slides where these come from. I just want to do an experiment. So here's what I'm going to do. So this is a depth 12 ResNet trained on CFR10 using SGD. The test loss is a function of epochs. Epochs meaning, one epoch means I go through the data set once. So that's basically what that means. And this is basically how the test loss behaves, okay? You're seeing a number here, n is 64. 64 means the number of channels that this, convolutional channels that this network has. It turns out in a convolutional architecture, the analog of width is a number of channels. So think of this as some parameter of width. So now I'm going to scale this network up, meaning increase width 2 times, 4 times, and so on and so forth. And when I'm going to do this, I'm going to do this based on these two prescriptions. I'm going to either divide my initial weights by a square root of n or n, depending on which one I commit to. So if I scale this network up using the NTK parameterization, the lazy parameterization, as I'm getting these bigger and bigger and bigger networks, you see that basically test loss starts falling slower and slower and slower. Okay. If I start from the same baseline, but scale up using the other procedure, which is going to the rich and mean field, or whatever you want to call limit, basically I get better and better performance. So I want to point towards multiple things here. Okay, so first, I'm approaching, first of all, I mean, I do get better performance, but it's not getting like infinitely better. It seems to be saturating, right? Reaching some kind of a limiting behavior. We agree, I guess that's, hopefully that's agreeable. The second thing is I want to point to a consistency in training. So for example, you're seeing that these kinks that you get in test loss curves across all these different training coincide, right? Now this is happening because we present the data in exactly the same order, these networks. So if we didn't do this, that wouldn't happen. The data is presented exactly in the same order. So what I want to say from here is basically, it sounds like as if these networks are approaching a limiting consistent behavior kind of thing, right? And then this is happening, this is a model that would fit in a A100 GPU. So this would be happening, you know, in a basically laboratory academic setting, training, you know, these kinds of data sets to basically a good performance. So this limiting behavior itself will be described by hopefully a DMFT or not. We'll talk about this, but basically, yeah, so that you're getting close to a behavior. So the final point and main point actually I want to make from this plot is basically different initializations and parameterizations. As you scale them up, give different behavior, right? So, and again, Andrea gave a very nice theoretical example of this happening. This is also a numerical point. Okay, yeah. Same initialization mean, no, we just randomly sample yeah. Cool. Okay, so let's think about parameterizations. How would you do this? Okay, so let's do a few notational things.
Question about the previous curve. What happens if you go on training, at some point test loss goes up? Are you going to say more about what happens if you overtrain?
We'll get there, yeah. Yeah, I mean, I've never seen this going up, so, but it will saturate. Now, I should say that this is a different training paradigm, so we'll say a bit more things about this. I'll get there. Okay, good. All right, so let's commit to a bunch of notations here. So we're going to be working with a data set. So this curly D will be the data set itself. It will come in pairs, inputs and labels, X and Y. And I'll, use my physicist notation of labeling them with a Greek index mu, goes from 1 to P. Unfortunately, P is something different in statistics, but we'll stick with this. Training will be, for the moment, gradient descent. We'll take one gradient updates. Okay, so this is how I would write the functional form of this, basically, neural network, right? So in goes an X here. Gets I'm omitting biases to make life simple at the moment. It gets multiplied by some weight matrix and becomes a hidden layer pre-activation. So that's what this is. And that goes through a nonlinearity phi, gets multiplied by a bunch of weights and becomes the next layer and so on and so forth. You can iterate. And then you take the last layer pre-activations H. And basically, so I call this, okay, so this is actually the same thing as the readout layer. I'm introducing another extra factor of scaling to read out from there. We'll see why that's an interesting thing to do. Notice that what I've done here is basically I've introduced factors of n wherever I think I could, right? Up to some powers of A1. For example, I've also chosen a bunch of variances for like the initializations that also depend on powers of n. I've also introduced powers of n in the learning rate itself. Okay, and this overall scale over here has also its n to the power something. Okay, so eta 0 and gamma 0 here are order 1 constants, and the other things how they depend on n is basically printed out. This d here is the dimensionality, capital D is the dimensionality of this data. I'm not going to touch data. Data is going to stay as itself. So this is just a notational convenience. Don't have to worry about that at this moment. Okay, cool. So this is basically, I'm committing to, of course, power laws. You could also think about other functional relationships and so on and so forth. But basically, this is where every place I could insert a power law or power of n in this. The question is, as I'm taking n to infinity, right, what choices of A, B, C, and D lead to a well-defined B limit? How many such limits exists? And so on and so forth. This is what we're going to ask. Okay? So this is what I'll call a parameterization and initialization, basically. Any questions about this? Cool. All right, so what do we mean by a well-behaved? Okay, how should we choose A, B, and C's and D's? So, okay, so then we have to come up with a definition of what means to be well-behaved in this limit. So we have to come up with some criterion. So there's a bunch of criteria that people have been using in the literature. So this particular three set was introduced by Greg Yang and colleagues in trying to get like what's called the mu-p parameterization. We have our version of getting to the same thing, but I want to point that this actually turns out to give you the mean field parameterization for two-layer networks as well. So there's some commonality in all these works. But let's just go through what we're talking about here. So the first thing you might want to require is a stable initialization. What do I mean by this? So you don't want basically when you initialize your network, the hidden layers to blow up, right? At the end, we want to put this in a computer, right? So that's important. So what you might want to require is that basically these hidden layer pre-activations, once you initialize this neural network, basically is of order 1 as you scale up. Likewise, for the output, now I use a theta notation and a big O notation because I want to allow, f to go to 0 as well, but that's just a technical point. Okay, so that's the first one. So this is about initializing the neural network, but you have to also come up with, criterion about training. And the reason is because of the following. As you are scaling up this neural network, right? I mean, depending on what factors of n you increase here and there, everything about this network will get affected. For example, the gradients that you calculate might get affected and so on and so forth. So you might end up in situations where actually the network doesn't train at all, meaning, the gradients just go to 0, or other situations where gradients are too large and things become unstable. So you have to be careful about this as well. So what we want to require is basically the output also evolves in finite time. Okay? One way you might want to impose this is basically by saying, that in every gradient step, the magnitude of this also stays order 1 with respect to scaling width. Okay? All right, so these two desiderata are satisfied by both feature learning and also the lazy limits, actually. So, okay, because the lazy limits also train and also have stable internal representations at initialization. But this final one is basically a distinguishing feature about the NTK parameterization and the other ones. And I'll call this feature learning. Now, feature learning might mean that you're learning beneficial features. I don't mean anything like this here. Okay, what I mean is just basically the fact that the internal layer representations themselves are also changing with time. Okay, I mean, we hope and practically we see that they evolve in a way that allows us to sort of perform better, but that's not a requirement at this moment. So HIL is again ith neuron in the ith layer, and I want basically its updates to also not go to 0. So in the NTK parameterization, for example, this will just go to 0, and therefore you won't get like a. All right, so imposing these constraints or the desired properties on this A, B, C, D gives us basically a constraints on them. Okay. So actually, there's one calculation we can do together. It's a simple, so I can just do it together and can see how this works. All right, so for this slide and perhaps the rest of this talk, the brackets here will actually mean an average. Okay, so that's what that means. So in this case, I'll be averaging over initial distribution of W's, which is some constants. So first, for example, let's look at what happens to. So this is an average over many different initializations. Okay. Let's first of all let's look at what happens to, let's say, a first layer pre-activation. Let's say responding to a input x mu. Okay, the ith sort of neuron there. So this is given by this functional form. Now I'm going to be averaging over weights because this is just a Gaussian with 0 mean. That's 0. So you can calculate the second moment here. It's a simple calculation, right? So just we're looking for h mu I, h nu j at the first layer. This is again two different neurons, I and j, responding to different inputs. So we can just write this out. Basically, you plug in the correlation here, which was given by a factor of 1 over n to the power b1 and so on and so forth. And there's a factor of 2 a1s coming from this normalization over here. So you end up with this. So what you want is basically this correlation or covariance to not go to 0 or blow up as n goes to infinity. So therefore, that immediately gives you a constraint on A and B, right? So you can just keep doing this layer by layer. Okay, for example, we can just look at the mean at the second layer, which is this is now there's a little subtlety here. So we have to do an average over this sort of term over here. Now the W, so this H also includes a W, right, coming from the first layer. But because we are at initialization, these are sample IID and independent. There's no correlation between them, so we can separate these and just move on. After a few gradient steps, they get correlations, these weights, because you have learning, so you won't be able to do this, then life becomes more complicated. But anyway, so you can do the same calculation for the second layer and so on and so forth. I'm not going to belabor the details, but at the end of the day, you're going to get basically a bunch of constraints on what these constants A and B should be. The idea being that you want these correlations to be order 1. Okay, so you can do similar calculations for basically these other desiderata here. Just to remind you what they were. Training meant I want the outputs to change, and feature learning meant I want the internal, pre-activations to change. And then, so basically you get basically like a set of conditions given by here. Yeah. Is constant. I'm just choosing a data set. Give me MNIST or something, and I'm using that. I'm not scaling it at this moment. I'm just scaling the model.
One question. Why are we scaling the learning rate here?
Why am I scaling the learning rate?
Yeah.
I mean, if I didn't, if I didn't, I might end up in a situation where actually the network doesn't train because the full gradient term update has factors of n. That might go to 0 or may not go to 0, depending on what you do here is important. I'll comment on this just now in a second. More.
Send variables very fast, but is it true? I mean, is it just a feature of the two-layer network, these two hidden layers, that you got a unique value of A's and B's, or could there be multiple solutions?
Let me exactly answer that question now perfectly. So first of all, this could be any layers. I just picked just 2 layers. Okay. So these constraints actually is one short than the number of variables I introduced here. So it leaves me 1 degree of freedom. Okay. So for example, I could use that degree of freedom to choose my C and D such that the learning rate doesn't scale with n, which would be a great thing if I'm doing this in a computer. And that particular choice actually exactly corresponds to the μp parameterization. I like to work with another case where, I mean, the n stays over there. But the point is, this 1 degree of freedom, they all, the dynamics that's described by this at infinite size limit is actually exactly the same. It's just a reparameterization invariance. Cool. Yeah, so, I mean, if you're interested in the full details of these calculations, you can look at this paper. We have our version in this paper. And then a few years ago, I wrote lecture notes on basically all that stuff. So there's a full description of all of these things over there. Okay, cool. Good. Yeah, so summary, this is what I just told you before. The difference is basically, so all that boils down to this particular figure, the difference between, so the difference between these 2 regimes can be calculated by introducing this gamma 0 factor and whether making it order 1 over root 10, which is going to put you in one or the other limit. In a second, we will basically vary this gamma from like small to large to be able to get these networks from feature learning to laser regimes. Good. Okay, so it was an observation by Greg Yang in his original MUP paper that basically this feature learning limit achieves, the hyperparameter transfer property. So this is what's called the standard practice, which is close to NTK, not exactly NTK, but okay, the idea is that basically he was plotting that like a log of learning rates on the y-axis training loss for different networks with different widths, and was pointing that you get the optimal learning rates for these models do not align. But if you're working with this in the feature learning regime, like basically you get like an alignment, and therefore like you can do hyperparameter transfer from small scale to large scale. Now I should comment at this stage, even though I wrote some papers in this by myself, I was going to talk about why why this particular regime. So the exact connection between hyperparameter transfer and being the feature learning regime or not, or parameterization is not exactly clear, I'll say still. And I'll say more, yes.
Here, what are you using for C? Because C and AL are coupled, but they're still free. You haven't fixed C to be anything in your learning.
I mean, what am I using for C and here?
Yeah, so are you fixing C to be something along with A1 in the plots that you're showing?
Yeah, okay, so let me say it again. So the number of equations here is one short than the number of variables here, okay? But they all describe the same dynamics in the infinite limit. So there's a 1 degree, so you can choose, you can commit to whatever you like. One practical choice is basically introducing an extra condition such that this learning rate is also order 1. That will add an extra condition, and that will uniquely fix all these coefficients. Okay, I mean, in my talk, I'll choose a different choice for these parameters, such that this scales with n, because of, you know, that's how we wrote original papers. and it also allows, so let me point to another one. If you don't do it this way, then there is some difference between how you initialize the first layer and so on and so forth. So we don't want to go into that. Cool. Okay, good. Okay, good. But then we might ask why, I mean, why is this happening? So let me show you a bunch of more experiments. Okay. So I don't really have a analytical sort of argument to this, but a lot of empirical studies we've done in my group on this work shows that basically, you know, if you're in this kind of parameterization, you approach very quickly and at scales that are approachable or available to a researcher, right? So all these experiments that I'm going to show were done in 1/800 GPU. Okay, you approach very quickly a consistent behavior. What do I mean by this is like small sizes are sort of behaving very. Okay, well, meaning that like you start to see a saturating behavior even with the largest model that you can see in A100. So this is again some experiment here. I'm plotting test error as a function of training steps, and you're seeing as even I'm scaling my neural network up and up, I do see consistent behavior in the sense that even the learning curves, the kinks and stuff align. So here's a more striking example. So what this is basically a true logit on a test point. So what we do is during training, we stop this network at every few time steps and give a test point and read out the logit value at the end of one of the logits, okay? And plot that. And what you see is a function of training steps. And then I have 21 minutes left. Is that what that means? Oh, wow, okay, good. As a function of training steps, and basically the logit value that you see over here is again, very, very, very consistent. Okay, cool. So it sounds like basically experiments that you can do at small scale could easily carry out to large scale. You can see similar things. For example, you can plot pre-activation histograms. These are histograms. What you do is you collect H's across a layer, and then basically you make a histogram out of it. And then through all sort of test data points. And basically you see that like across different widths at initialization and after training, they coincide. I'm also pointing to this because this will come handy when I'm starting to talk about mean field theory. And even like similarity matrices, these are just like kernels, layer kernels that you calculate across different widths. They look very, very, very similar. Good. Okay, so just to conclude here, so we talked about two different parameterizations and mean field and so on and so forth, and one of them gave hyperparameter transfer. And notice that this didn't require, you know, even though we could and we will, a sophisticated calculation, just back of the envelope, scaling arguments to settle this up. So let's try to see what we can say about like a more sophisticated architecture. I'm skipping a few architectural steps, so I'll just try to go to the transformers. And so here, I mean, of course, I mean, the architecture is different, right? So let's think of a particular version. Maybe we're alternating, like, you know, a multi-head attention with MLP blocks and so on and so forth. And there, you know, residual connections and skip connections and all these kinds of things. You know, and then many things you could scale, right? But basically, like depth here, you know, again, you know, number of heads, dimensions per head, and so on and so forth. So there are many things that you could do. As this is just pointing out like what happens in the just a schematic of what happens in the multi-head attention layer. Exactly. There's a bunch of things you could think about, like scaling up. So what do we do here? Okay, so we worked out a bunch of these, things, the heads and head dimensions and MLP width and depth scaling and initialization scale in a series of papers. So these are from my group. This is from, again, Greg Ng and colleagues. These two papers were looking at ResNet-like architecture with skip connections. And this paper was looking at basically architectures with self-attention layers. And then, there was some theory developed. And lately, in this year, we published an article in collaboration with Cerebras Systems. So this is a startup company that has access to large-scale compute, where we basically tested some of these parameterizations. And I'm going to show you some results about like how they behave and why they behave. Okay, but first, let me point to. So I'll follow the logic in this paper. But if you're looking for which is more hand wavy and like intuitive, but if you're looking for more theoretical stuff, it's available in those papers. Okay, so here's the basic setup. Again, what I'm trying to do is basically figure out a way to scale things. Now, I'll assume that I figured out how to scale width. I'll just think about how to scale depth. So I'm not going to go very deep. This will introduce actually one interesting phenomenon we're going to talk about. Okay, so the idea will be the following. In this kind of architecture, there is this residual sort of steps, right? So the pre-activation in one layer basically directly gets the activations from a previous layer. And then also through information passes through some kind of a neural network. This might be an MLP or an attention layer and so on and so forth. Okay, so this is how the architecture goes deeper and deeper. Okay, good. So what we want to figure out is basically like how to scale. The L is the width, depth. We're going to go things deeper and deeper. How to scale, with what factor of L should we scale this particular contribution here, such that things behave well-mannered way, you get feature learning and all that kind of stuff. And for this particular 3 slides, I'm actually going to do with this Adam, not just gradient descent, but we're not going to go into the details of what Adam does, just how the paper was written, so I just want to be consistent. Okay, so let's think about this data again. So what do we want to achieve? So first, again, stable initialization. Hidden layers and output should remain stable at initialization. What that means is the feature, again, like the pre-activations or their norm should be ordered 1, and so on and so forth. Okay, so it turns out what this immediately leads to is a constraint on that L to the power alpha. Alpha should be greater than 1/2. It's again a quick derivation we can do here. But let's just commit to a particular case of this. I don't want to go to the full thing. Basically, we're doing MLP kind of a ResNet here. Okay, this is by W is basically scaled in a way that I know is basically stable with respect to width. I want to figure out what this L is, or L to the power alpha here. So at large N, at large width, basically I can think of at initialization, I can replace this with averages over the W initialization, and basically I get an iterative equation like this. Okay, about the norm of a particular layer. Just again, I'm trying to get there to where I want to get as quick as possible. Let's just set phi to be a ReLU, okay? And that gives you an iterative equation in terms of the norms of each layer of this sort. And you can calculate the limits easily. And you'll find that basically if it's alpha because of this power here, again, if you so remember, this is going to be iterated capital L times. If you expand that, and you get basically the L multiplying this L to the minus 2 alpha, and you want that to be stable. So exactly that basically ends up giving you these constraints. If alpha is less than 1/2, this iteration goes to infinity. If alpha is greater than 1/2, and actually you just read out the initial, nothing happens, and then you get some factor of some alpha is equal to 1/2, you get a factor in front, and so on. So that's the constraint. The second constraint, the second desideratum is basically, there's a technical name we use for this, maximal residual stream update. What that means is each residual block's weights should contribute to order 1 over L to feature movements, and each non-residual block should contribute constant order. It's a technical statement. I'm not going to go into the details of this. Just mention what this means in words. What this means is I want basically intermediate H's to train. This is the same condition as in MLPs. This is the feature learning condition and outputs to train. It turns out that basically puts a constraint on my learning rate to be of this of the scaling. And the final one is the interesting one. So this is a new thing that didn't appear before. I'll call this complete feature learning. Okay, so let me first read the technical statement. The network parameterization satisfies complete feature learning, meaning neither the hidden layers nor the model output F are lazy with respect to any subset of model parameters. What do I mean by this? So let's think about like the linearization. So this is basically, I'll call this quantity. The linear is actually be a vector as well. The linearization, the linearization of a particular pre-activation layer. Okay, so what we're going to say is basically if this is a particular layer is lazy with respect to a subset of parameters, if at finite depth and width, HL is not linear in theta, and the change on that layer at initialization from updating only the parameters is asymptotic of a particular set of parameters is asymptotically the same as the change to linearization of H. So basically, there's a particular parameter that I'm changing, and the changes in that pre-activation is the same as the linearization. I don't want that to happen. The reason this is I'm asking this extra thing, okay, is because of the following. This is a technical constraint, but it will be, let me just work through a example and you'll see why this was necessary. Get the question?
The question I had was that in the case where you're in the over-parameterized regime, there's clearly some combination of parameters that gives you a flat direction on the data that you have, right? But you're not demanding that there shouldn't be a combination of parameters. You're just saying in the parameterization you have, it shouldn't be lazy with respect to any subset. Because you're almost guaranteed to have flat direction. I mean, you are guaranteed to have flat directions in the over-parameterized regime. I'm just saying your gradient is in a very high dimensional subspace because you have, and you don't have those many data points. So surely there are vectors you can find that are orthogonal to your gradient.
Now that is true. Yeah. All right, let's talk about this after the questions. The bold H is a pre-activation. No, just one. Yeah. Well, we want this to happen for every data point, actually, so that's the idea. But let me give the example. So let me come back to this and let's talk about this. Okay, so let's look at a very simple depth two example. So I'm actually not going to even consider like an infinite width, just take n equal to 1. And then update this W2 and W1 with some updates. So let's look at the change in this guy, and that can be calculated by simple just to linear order in Taylor expansion. Okay, so here is an interesting observation. This is just the updates on the weights, and then I'm going to second order. And the reason is because the first order basically changes just a linearization change. Right? So what I want is basically the second order change here as I'm scaling L to basically to be of the same order in L. Now, the point I want to make is, so there's one thing I didn't show or agree or discuss. Basically, from the first two days data, you can also show that like these updates should be of order L to the alpha minus 1. The point is, the first term over here goes like L to the minus 1. The second term over here goes like L to the alpha minus 2. What that means is basically if alpha was, less than 1, right? So what's going to happen is basically this term is not going to contribute, and you're going to end up with basically like the changes being identical to as if only the linear part was changing. Okay, so the intuition here is the following. So basically, there's a danger here. So when you're going from layer 1 to the next layer, right, there's two streams, the direct part and the residual part. Residual is an MLP. What might happen is basically this MLP in the infinite width limit can become a lazy network, right? So it's actually not learning any features, but it's basically learning its updated output. So you don't want that. You want basically within each block, the MLP or the attention layer, whatever it is that you have over here, also to learn features. And that's exactly what this is trying to prevent over here by introducing another scaling factor over there. And you can show in simulations. We're going to show that in a second. Okay, good. This works. But here is basically, a whole set of parameterizations. And basically, including some parameters of Adam and MLP stuff, and all the factors of L and N and so on and so forth. You might want to introduce to get these different limits. Now there's a choice here. Alpha can be anything between 0.5 and 1. Our claim is alpha is equal to 1 is the best, and then and so on and so forth. So it's a lot of stuff going on over here. Yeah. Cool. But I just want to point to the same idea here, the practical benefits idea. So if you do choose the things this way, the validation, so you do get like a stable hyperparameter transfer across depth. So that's good. So this is an interesting, basically, comparison. So we are comparing flop savings with respect to mu-p initialization. So this is the one that didn't have this depth aware behavior as a function of depth of these networks. And then basically you're seeing different parameters, it's 50 million, 300 million, 1.5 billion parameter models. And then you're getting basically like improved savings. And this one is basically another aspect of this. Now, when you're trying to do these things, you have to come up with an aspect ratio, width versus depth, how much wide and how much depth should be. And this is quantifying the like an optimality region for width and depth ratios. What that means is like how sensitive or insensitive you are to that. And you get a wider sort of efficient width to depth ratio for basically this kind of parametric comp-EP, which we call this parameterization comp-EP. Okay, so just to conclude, basically different parameterizations and initializations lead to different behaviors and scaling limits. And parameterizations that allow predictable and consistent scaling offers hyperparameter transfer benefits. Now, of course, I mean, this was all done using, architectural, the particular architectural choices. As new architectural details come, you might have to rework all of these things. And then, for example, mixture of experts and so on and so forth. Okay, so, questions?
Here, we did not specifically consider anything about the data itself. So, like the choices and parameterizations we choose here will be the same for any data set. Like it's independent of.
Yeah, data. As long as okay, so as long as data is well behaved, in the sense that norm is not flowing to infinity or something, that's fine. Now, a subtlety might arise if the data becomes low rank or things like this, but like, yeah, so for practical sets stuff, you're fine. Okay. Now, there's another place where this might change if you're scaling the data set size as well, or the data sets. So if you're coming up, let's say, with like some problems where you have analytical control over data and you want to study like, dimensions going to infinity or the number of data points going to infinity, like Andrea discussed, then basically you don't end up in these scaling limits. You end up in different scaling limits. Well, I'll say something about this when the time comes up.
Yeah, so I guess more questions about this data problem. So whatever you said is about the training log, right? But we also, or is it also?
So these are, so these are trained, okay, so these are trained in an online manner. So the experiments that I'm showing you are basically cross entropy in online training. Right, so I just give you like data, you do one pass, and I'm giving you the loss report and to you the loss basically on the last some trailing set of data. I think in that sense, basically, you can treat those last guys as like some test kind of a loss as well.
If I understood correctly, you're also doing some validation. So you're plotting the validation loss.
There's no validation loss here. It's just the experiments I'm showing are like the entropy training loss. Yeah, okay. On one pass.
Sorry, I'm not getting the answer. So I guess I'm asking that. So whenever we talk about loss here, which we're trying to minimize, is that training or is it a test? I guess eventually.
Okay, so when I was talking about these plots, these ideas, I was talking about train loss.
Yeah, sorry.
Okay, the experiments I'm showing you are not in a different setting.
Okay.
Okay, they're just done in a setting that will be able to in practice. That's what I'm showing.
Okay, maybe let me ask you in a different way.
Okay.
So I guess whatever you said shows that that indeed, if we do the hyperparameter transfer in this smart way, then you get all these nice properties, and very good. But I guess maybe it's similar to what Andrea was doing and stuff. That so maybe you also want to convert to the correct W star and all that. So
I'm not assuming. So this is done on real data, right? I don't know what W star is. This is CLMPJ data set. There's no data generator here. These are all done on Wikipedia or something like this. In this particular case, the CLMPJ data set.
Okay.
So I don't really know what the W star is.
Related to that, I guess we have the desiderata that you have here. Like, why do we think those are the correct desiderata? Maybe there
That's
could be some
excellent
other
question. So we don't know if this was the correct desiderata at all. I mean, you can come up with your own. Yeah. So, but I mean, so the intuition here, or the thinking here is basically we want to maximize feature learning. Whatever that means is basically you want to make sure all parts of this network, all the representations, whether you are within the MLP block, within the residual block, or something, they move. So you're thinking that that's basically that's going to get you better results. But there's obviously, this is not a proof that this will work this way.
I guess like eventually
empirically, for example, the alpha, I don't show it here, but there's a version of this where the MLP block freezes, becomes lazy, and then you don't get these nice properties. But yeah.
I guess eventually the desiderata should be empirically validated whether those are the best desiderata.
Yeah, so I would say the results are basically, this is the result rather than math I showed, yeah. Cool.
Perhaps I missed something. When you state these desiderata, these are for one step of full batch gradient? These changes are
right. So, very good question. Okay, so technically you want this to hold overall training. But obviously, I mean, calculating these things for the full training is hard because you pick up correlations in weights as you train. So all the calculations that I'm showing here are basically done with the first step assumption that basically that like the weights are not coupled.
I wanted to understand this is full batch, is not
full batch. Full batch. Now we do have we can have a mini batch versions of this too.
Okay.
You can there's probably a batch parameter here. I should check. Yeah. Yeah.
Actually, one more thing. So I guess like in Andrea's work, he showed that like as we keep on training, the model transitions from say mean field limit to NTK limit and so on.
Right.
So and for that, like we really have to train for longer amount of time.
Right.
So here, like we are analyzing only for a few steps of gradient descent, and then we are requiring that like it remain in the same, like it satisfy the same.
Right. So I mean, okay. So
desiderata.
That's a great question. So I haven't actually talked about anything about characterizing the limit. I just give you a bunch of heuristics about how to choose initializations and maybe one step and then to see how to do it. Right? So the question you might ask is basically, okay, let's see a learning curve. I might even show you something, but just give me 1 second. Okay. So what happens, for example, like if I train more and more, okay, are these networks staying in this particular regime or not, the limiting regime? Okay, so I was going to talk about, I'll talk about more in this in detail next time, but I just want to point to one thing. So this is again a bunch of experiments that I'm showing, imaginative text trained on some transformer architecture and so on and so forth. Okay, so there's a question to Andre in the morning as well. I think one of you guys asked, what is the rate of approach to this particular limit, right? And you said like it's a central limit theorem kind of thing. Okay, good. So basically, what you would expect then if your approach is a central limit kind of thing is basically, you know, this. So these are different widths. The network has different widths. So if I were to plot these guys on a, you know, log plot, I should see a slope that goes like 1 over width. And then, so I'm going to show you that plot. Okay, cool. So basically, what happens is later in training, okay, so this is after a bunch of training steps, I'm plotting these guys in basically as a function of width and the test loss, okay? And then basically what you're seeing is that the scaling exponents are not 1. Let me show you one more experiment and I'll come back to this. So this is another experiment where I'm scaling attention heads. That's a different thing, okay? The test loss attention heads, these are networks of different size. Now, in this particular experiment, we were smart and we were able to plot these curves at different sort of points along training steps, meaning early versus late, okay? So during early in training, basically, if you were to plot these curves, put these curves on like a log plot, you will find that, I mean, the approach is more like a 1 over n, okay? But later on, basically, you get to fall or n scaling, which is not. So, so it's a fact that even if you start these networks by, you know, very close to this regime, you know, over time, they may or they may not basically. So I take this deviation from 1 over n fold as basically going out of this particular scaling regime. And then depending on the data set, so for example, this doesn't happen if you're doing CFR10 or MNIST. So there's a there's a data set complexity issue here as well, which I don't know how to control. But depending on what data set and what architecture looking at, usually early in training, you know, you're consistent with this kind of a scaling, but later on you go away from it. So that's what we see in general. Right. So now, is this basically so? What's happening here? What kind of scaling regime is this described by? I haven't said empirical question, so I mean I'll try to say something about it next time. Yeah, you can try to see this kind of exactly this kind of behavior in linear models as well. So I'll try to demonstrate this, and this will answer that question more concretely in that particular setting. I'm not able to give you concrete answers for the experiments I showed because these are very empirical studies, but hopefully tomorrow I'll give you one thing I can exactly solve and tell you what happens there.